Inside the Sun, deep in the Earth's core, inside every fusion reactor, there is a fluid that carries a magnetic field with it, and simulating that fluid is one of the hardest problems in computational physics. Magnetohydrodynamics is the physics of fluids that conduct electricity. Move the fluid and it drags the magnetic field along with it, stretching and folding it. But the field pushes back through the Lorentz force, so neither one can be solved on its own. They are locked together. That's the Sun, the Earth's core, fusion reactor, liquid metal cooling. And that coupling does something unpleasant. The flow squeezes the magnetic field into razor-thin sheets of electric current. They keep getting thinner, often finer than the grid you are computing on. Inside them, field lines snap and reconnect, releasing stored energy. Lower the viscosity, and the sheets sharpen further, until the solver simply falls over. The Lattice Boltzmann method takes an unusual route. Rather than solving the fluid's equation directly, it tracks packets of fictitious particles on a fixed grid. Each step, every packet hops to a neighbor, streaming. Then packets relax towards local equilibrium, colliding. Repeat everywhere, and fluid dynamics falls out. The magnetic field rides a second, smaller lattice, and because every operation is local, it runs beautifully on parallel machines. Everything hinges on that collision steps. The standard choice, BGK, relaxes every mode at the same rate, simple, fast, and fragile. Push the viscosity down, coarse on the grid, and it doesn't merely lose accuracy, it is destroyed. Here are two runs on the same grid, with the same equilibrium and the same physics. Only the collisions differ. And watch the left one. So what's going wrong? Split each population into an equilibrium part and a departure from it. That departure breaks into modes. The second order one carries the real physics, the stress. But the lattice also supports modes that mean nothing. Numerical junk. And that junk is what destroys the simulation. The classical fix measures velocity gradients, extra work, no longer local. Recursive regularisation is cheaper. Read the second order mode straight from the populations. Build the third from it, and the fourth from the third. Reassemble the departure from those alone, and the junk has nowhere left to live. No gradients, still local. The test is the Orszag Tang vortex, the standard stress test for magnetized turbulence. Smooth at first, then the sheets appear, the field reconnects, and the flow tips over into fully developed turbulence. Everything you are watching is a real simulation of this scheme, at Reynolds number 5000. On fine grids, the peak current and vorticity land within about 1% the spectral reference, level with the best collision models available. On coarse grid, the difference is starker. Where BGK is simply destroyed, recursive regularization keeps producing converged numbers. The energy tells the story. Magnetic energy builds as the field is stretched, then collapses, and the sheets reconnect, converted into motion. The higher the Reynolds number, the sharper the exchange, and the longer the turbulence keep going. None of this costs much. The extra Hermite work makes each step moderately more expensive, and the method stays local, stays a single relaxation time, and scales the way ordinary Lattice Boltzmann method does. What you buy is robustness, a usable answer on grids where the standard schemes has already failed. The paper and the code are linked below.